Hello and welcome. So, you've probably seen some headlines flying around about scientists using a quantum computer to find dark matter. And that's a massive claim, right? So in this explainer, we're going to dive into the actual research paper to figure out what it really says, what it doesn't say, and why it's still such a big deal.
The whole story really kicks off with this wild, almost science fiction idea. What if this annoying, persistent bug that's holding back our most advanced computers isn't a bug at all? What if it's actually a message from the cosmos? Okay, let's get into it. To even begin to understand that huge question, we first need to zoom way in. We got to look at a very real-world engineering problem that's been a major headache for quantum physicists for years.
Okay, so at the very heart of a quantum computer, you have the qubit. Now, the easiest way to think about a qubit is to imagine a perfectly balanced spinning top. For the computer to do its magic, that top has to spin flawlessly for as long as possible. That period of stability, that's called coherence. The longer the coherence, the more powerful the quantum computer. Simple as that.
But, and this is a big but, there's a problem. Researchers keep finding that something is knocking these little quantum spinning tops over. There are these tiny, random energy fluctuations, kind of like a constant low-level hum or noise, that makes the qubits wobble and lose their coherence way too fast. One of the main culprits has a technical name, quasi-particle poisoning, and honestly, it's a huge roadblock to building bigger, better quantum computers.
And this is where the story takes a really brilliant turn. A team of physicists looked at this engineering headache and came up with a completely radical new idea for what might be causing it.
They just asked the question, what if this noise isn't just, random interference from the electronics or something in the lab? What if it's the actual signature of dark matter, the invisible stuff that makes up most of the matter in our universe, passing right through the walls, right through the computer, and bumping into these super sensitive devices? So the specific theory goes like this. We know the Earth is flying through this giant halo of dark matter that surrounds our galaxy. What if, just maybe, one of those dark matter particles occasionally hits a qubit, drops off a tiny bit of energy, and causes that wobble we've been talking about? In that scenario, the qubit stops being just a computer part and becomes an accidental particle detector. Now that is a bold idea. So how on earth do you test it? Well, this is the clever part. The scientists used a method that isn't about finding dark matter, but about narrowing down the places it could be hiding.
To really get your head around this, let's use an analogy. Imagine you're in a pitch-black, silent room, and you're trying to find a tiny mouse. This study didn't hear a squeak and yell, "We found the mouse!" No. Instead, they measured just how quiet the room is, and then they said, look, we don't know where the mouse is, but we know it must be making less noise than this. They used the silence of the room to set a new rule for how sneaky that mouse has to be.
The actual scientific logic is just a really elegant piece of reasoning. First, they take their super-sensitive qubit and measure all that unexplained noise. Step 2, and this is the key move, they make a bold assumption just for the sake of argument. They say, what if 100% of this noise is from dark matter? From there, they can calculate exactly what dark matter would have to be like, its mass, its interaction strength, to cause that much noise. And that final number doesn't prove anything about the noise, but it does become a new upper limit for those properties of dark matter.
So let's be absolutely crystal clear, because this is the most important part. What this study means is that whatever dark matter is, its ability to interact with normal stuff has to be weaker than the level they just calculated. What it does not mean is that they detected dark matter. It doesn't even mean dark matter is causing the noise at all. They just use the noise as a yardstick to set a new limit on the quietness of the universe.
The specific measurement they used is called the quasi-particle fraction, or XQP for short. You can really just think of it as a number that tells you how much noise there is. The lower the number, the quieter the system. And the data they used for this paper came from a quantum system that was incredibly quiet, one of the quietest ever built, which is what makes the results so powerful.
So what did this new super quiet measurement actually accomplish? Well, it allowed physicists to literally redraw the map they use in their search for dark matter.
And this is the perfect way to visualize it. Imagine a huge map of all the possible properties dark matter could have. Different possible masses, different possible interaction strengths. What this study did was draw a new big line on that map and shade in a huge chunk of territory, basically saying, hey everyone, based on how quiet our qubit is, we now know dark matter can't be hiding anywhere in this region.
Now, this new boundary is especially powerful for theories about really low-mass dark matter. We're talking particles with an energy equivalent below 30 kiloelectron volts, which is just a tiny, tiny fraction of a single electron's mass. In that specific weight class, this study now sets the world's most stringent laboratory-based limit on how weakly this kind of dark matter can interact.
And you don't have to take my word for it. The authors themselves are very, very careful about this. They state right in the paper, and I'm quoting here, that the DM signal remains indistinguishable from other backgrounds. But, they continue, you can use these measurements to place world-leading bounds on DM interactions. It's very precise.
So if they didn't actually discover dark matter, why is this research making so much noise? Well, because it gives us a powerful new way to look for it.
So why does setting a new limit matter so much? A few big reasons. First, it ingeniously turns an engineering bug into a scientific feature, which is just awesome. Second, it gets to piggyback on the billions of dollars being poured into quantum computing research for a totally different scientific goal. Third, it opens up a whole new front in the hunt for dark matter. And maybe the most exciting part, as engineers get better and better at building quieter qubits for computers, those devices will automatically become even more powerful dark matter probes for free.
Okay, let's bring it all home and answer our original question. What does this study actually say? Well, given the paper itself, what we can responsibly say is this. No, they did not find dark matter. But what they did do was brilliantly repurpose existing technology to narrow the search, to rule out a whole new range of possibilities, and in doing so, they forged a new and really powerful path forward.
And that just leaves us with a pretty fascinating thought to chew on. We're building these incredible machines for one reason, but they're turning out to be sensitive to things we never even imagined. As they get quieter and more stable, what other whispers from the universe might they just happen to overhear?